There, that should be good. Sorry about that. So better multiplication. We started looking at this on, I guess, Wednesday since we skipped Friday. I gave you an example of the grade school method where, and we've got the same work that we were doing last time, where if I've got, say, two 4-digit numbers, right? You end up having to do ultimately 16 multiplications of single-digit numbers in order to multiply these two things together. And ultimately, if you're going to be doing this a lot, then this is going to be n squared, right? And is there a better way, right? And I'm putting better here in double quotes because in practice, it's probably not going to be better. And in fact, I'll show you a demonstration here that I did over the week, that I developed over the weekend to answer my own question on whether or not it is actually better in practice. So what I want to do is I want to revisit multiplication. Let's rethink multiplication, okay? So let's say 47 times 51, right? Now, again, if you were to write this out and do long multiplication, right, then you would have 1, 2, 3, 4 multiplications of two single-digit numbers, right? So let's split this up. Let's split this up into 4 times 10 to the first plus 7 times 10 to the 0. Right? Hopefully you all agree with me that that's 47. Oh, sorry, thank you. Hopefully you all agree with me that that's 47, right? Times 5 times 10 to the first plus 1 times 10 to the 0. Right? Again, we are on Piazza and we are on YouTube, so if you have any questions, please go ahead and post there. Otherwise, we all agree that that's correct math so far, right? Now, first of all, what about, let me go ahead and highlight this thing right here. Is this really a multiplication? Is this really a multiplication? Is this and this? Am I really multiplying by anything? It's just a shift, right? These are just shifts. So they really don't count as multiplications because they're a much simpler operation. Base 10, shifting, is just shifting the decimal place over. Base 2, well, that's going to be shifting is then division by 2, multiplication by 2. Same idea, okay? So what I want to focus on are these numbers right here. I'll highlight them in blue. 4, 7, 5, and 1. Now let me generalize this. Let me call them A, B, C, and D. Right? Forget about the shifts for now, okay? What do I have here? I have A plus B times C plus D, okay? Now, let's expand this out so that we can see, you know, if you were to actually do this as a long multiplication, let's see all 4 of those multiplications right in front of us, okay? So what rule do I apply to get all 4 of those multiplications? Distribution. What, isn't there an acronym for it? Maybe they don't teach that anymore. FOIL, right? FOIL. First, outer, inner, last. So this is going to be AC plus AD plus BC plus BD. Right? And how many multiplications do you count now? 1, 2, 3, and 4. Right? There is, now, on the left-hand side, I could get away with 1 multiplication technically, right? Well, no, not really, because you'd have to add those back in together, which would lead to a 2-digit number and a 2-digit number. These are still, over here, these are single-digit multiplications. Over here, this one, this is a 2-digit multiplication. So don't confuse those, right? You might say, well, wait, why are you doing all 4 of those multiplications on the right-hand side when you could get away with doing the multiplication on the left-hand side, okay? But the trick that I'm about to apply is going to be very, very similar, right? For example, so what we're interested in are these guys right here. Let me go ahead and rearrange and get those on the left-hand side and everything else on the right-hand side. So AD plus BC. There are 2 multiplications there. Let's go ahead and shift the other thing onto the right-hand side. That is A plus B, C plus D, right? minus AC minus BD, right? So sorry, what I meant was leave these over here. Take this and bring it over to the other side by subtracting it. Take this and move it over to the other side by subtracting it, okay? Now, how many multiplications do you actually see here now? I see 1, 2, and oh, did I screw up? AD plus BC. 3. Say it again.
Well, you have all the 2-digit multiples from
We haven't. No, we haven't. We've symbolically done it. We don't have any results at all, right? I need to get this correct. AB plus BD or CD. There we go. All right. So, all right. So here it is. Let me go ahead and highlight this in blue. All right, let's go ahead and pay for this multiplication right here and pay for this multiplication right here. That's 2, right? 1, 2. We will reuse them in this expression right here, pay for a third multiplication, and then we've got this thing right here that we don't have to actually compute 2 things for. Now, what I said before is it is a 2-digit multiplication, right? But it's not a 2-digit multiplication if we use recursion. Right? What we're going to do is we're going to cut it down. Right? In fact, that's what we did here. We cut this down, this 2-digit multiplication right here. We cut it down into single-digit multiplications. Right? And then we recurse. Only when you get down to single digits, then do you actually do the multiplications. So let's actually go ahead and write this out in full. Right? And this is all just still base 10 here. If I've got 2 digits here, each one of these are n digits, right? And n digits. By the way, if they're not n digits, if one of them is 50 digits and one of them is 10 digits, how do I make a 10-digit number into a 50-digit number so that it matches? Put a bunch of zeros there, right? And then when you recurse on it, what you're going to end up doing is you're going to end up having a 0. 0 times anything, 0 plus anything doesn't change. Right? All right, now here's the idea. What I'm going to do, what I'm going to do is I'm going to split these up into 2 numbers. A is going to end up being the first n digits and the last n digits. So this will be, I'll call this A1, and this will be A2. Or let's go A0, because that's what I do in the code, A0. Right? And here, there are going to be n divided by 2 digits. And over here, these are going to be n divided by 2 digits. So that A is equal to A1 times 10 raised to the n divided by 2 plus minus 1. Of course, there are details there. Plus A0. Right? Do the same thing for B. B will end up being B1 times 10 to the n divided by 2 plus B0. And again, A0, A1, B0, and B1 are all n divided by 2-digit numbers. Right? I don't know how to do those, so you divide and conquer again. N divided by 4, n divided by 8, n divided by 16, etc., until you get down to a single-digit number, in which case you just multiply those 2 things together. Okay? Now here is the actual full mathematical expression. If I split this up like I just described, it's going to be A1 times 10 to the n divided by 2 plus A0 times B1 times 10 to the n divided by 2 plus B0. Right? And I'm going to split those up using that FOIL trick that I just showed you. That this is equal to A1 B1 10 to the n plus, I'll go large here, A1 B0 plus A0 B1 times 10 to the n divided by 2. There we go. Plus A0 B0. Not shifted at all there. This middle part, that's where you can reuse this first part and this second part, all right? So the first part and the second part don't change. And the last part doesn't change, sorry. A, B naught, there we go. Plus, and now how can I expand this out? It's going to be A1 plus A naught times B1, B naught, minus A1, B1, that first one, minus A naught, B naught, that second one, times 10 to the n divided by 2, and then plus here, okay? This is the FOIL trick right here. Now make your observations. How big are each one of these numbers? This is 1, 2. 1 and 2 are 2 n divided by 2 digit multiplications, right? We reuse them here and here, right? Now what about this thing right here? A1 plus A naught. So A1 plus A naught. Oops, sorry. How many digits is that? Remember that we split them up into two parts. N divided by 2. Add them together though, and they could be with overflow. Could be as a n divided by 2 plus 1 digit number. And same observation here. B1 and B naught is an n divided by 2 plus 1 digit number. Therefore, 3. Number 3 is a 2 n divided by 2 digit multiplication. Right? So instead of 4 multiplications, I've cut it down to 3. Right? Now, does that help me? What we're going to have to do is we're going to have to set up a recurrence here. This is called Karatsuba multiplication. Right? And what I'm going to do is I'm going to set up a recurrence. M sub n is going to be the number of one-digit multiplications made by this algorithm on 2 n-digit multiplication numbers, A and B. Right? Now, m divided by n. What I need to do is I need to set up a recurrence for that. How many multiplications did I end up making? 1, 2, 3. And they're all roughly on numbers that are about n divided by 2 digits. Plus 1, forget about that. Don't worry. Right? So I make 3 multiplications recursively on digits that are n divided half as big. Right? Now, did I make any multiplications non-recursively? Let's come back over here to this expression right here. Do you see any other other multiplications that I made?
The 10 and...
This one right here? Now, again, is that a multiplication, technically? Not in base 10. It's going to be a shift over, right? And if you were to do this in base 2, of course, then instead of you would cut it into bits, roughly, if there are n bits, then you would cut it into the the highest order bits over here, the lowest order bits over here, and then you would shift everything by a power of 2 instead. Right? So, it's weird, but no, we don't make any multiplications at all. Right? So don't get the idea that that means that this algorithm is free, that it's constant. Apply the master theorem. Right? We have A as being 3, B is 2. What is D in this case? This is going to be a polynomial of order n to the 0 because it's constant. So D here is 0. So A, which is 3, times, or versus b to the d, a is clearly greater than. So does anybody remember that case of the master theorem? If not, I'll pull it up really quick. There we go. There it is. That case is what? The third case. So case 3. And we have that Karatsuba multiplication is order n to the log base b, which in this case is 2, of 3. Okay? I'm going to go ahead and delete this so that it's not in the notes since you have it before. Okay? Does anybody want to pull out their calculator and tell me what that is? Or I could just look it up. I don't even know.
The log base 2 of 3?
Yep, it's going to be approximately order n to the 1.58. Of course, it's not a rational number, so it goes on, right? Now, is that better than the grade school method asymptotically? Yep,
Probably.
because the grade school method was what again? N squared, right? So we've cut it down ever so slightly. But is that, I mean, the question is, it's a small, it's an asymptotic improvement, yes. So from a theoretical point of view, it is an improvement. I've always told students that, yes, it's a theoretical improvement, but in practice, would you do something like this? And probably not. And so just to demonstrate it, I actually implemented it, and to remind myself how it worked. I implemented it over the weekend here. I did design a base 2 version. We'll come back to it in a second here. But here it is, right? So we want to increase the size here. First of all, there are some corner cases that you have to take care of, right, in practice. For example, if either a or b is 0, you're done because you're trying to multiply a times b, and so if one of them is 0, then you return 0. Otherwise, I get the number of bits, or in this case, sorry, this is a decimal version, so I get the number of digits in one of them. It doesn't really matter which one is which, right? Again, the idea here is if you have a 50-digit number and a 10-digit number, you really have two 50-digit numbers. These are all just zeros out front, right? Implicitly zeros out front. If we get down to a single-digit number, a is only a single digit, then we simply just return a times b. Right? Otherwise, I get the power, right? And what this is this is n divided by 2. So this is 10 raised to the n divided by 2. That's how much I'm going to shift it. And then I split it up into A1, A0. Right? This is the higher order digits. These are the lower order digits. Higher order digits, lower order digits. Right? All I'm doing here is shifting it over, and then shifting it back over, and then subtracting it from the original number. Right? Okay? Then I make 3 recursive calls for each one of those numbers that we just described. Right? Over here. Where was it? Right? I need to multiply A1, B1. I need to multiply A0, B0. And I save those off into 2 variables. In this case, x and y, because I'm going to reuse them. X and z, x minus z. Minus x minus z. Okay? And then I perform Karatsuba multiplication on those 2 sums. Right? Note here I'm not multiplying them. I am passing them off to a recursive call to this function. And then finally, I shift x over by 10 to the n divided by 2 times 10 to the n divided by 2 gives me 10 to the n. So I shift it all the way back over. I shift the middle one over by 10 to the n divided by 2, and then I don't have to shift the lowest order digits at all. I've tested this rigorously, and just like you were discussing testing before. I generally, what I do is I generate 2 random digits, 2 random numbers with approximate up to 2 digits in this case. You can, of course, set this over to 100 digits or something like that. I'll go ahead and keep it at 2 so that we can actually read it for now. Then I time it. I time this Karatsuba, and of course, I make sure that it's correct by actually just multiplying x and y together. Right? And I also time that, by the way. I found that it sucked. Right? And so I thought, well, it probably sucks because I'm doing everything base 10. In a computer, everything is really base 2, right? And so if I did a bunch of shifting base 2, that's going to be way more efficient, right? So I did Karatsuba binary version of it, right? And I got the number of bits in it. And if the number of bits is less than or equal to 1, then I return A times B. Otherwise, I shift things. Right? Now I'm using bitwise operations instead in Python. I shift things over. I shift things over and back. And I shift, by the way, I only did this because I had to force all the operations to actually be integer operations. And to do that, sometimes they switched over to floating point numbers, and so it failed. Anyway, some of these things were hacks because of the way that Python works, or at least they weren't documented anywhere on how this stuff works. And so through trial and error, I had to get it to work by, all right, fine, I won't use the math library for that. I'll use it, for example, I was originally using POW to do shifts, and it wouldn't work. My suspicion is because it's using the actual C implementation under the hood for POW, and thus you're losing, it's overflow and you're losing precision. But if you use like ***, then that keeps it within Python. You're not using those things that result in overflow or whatever. But in any case, it turned out that it was even worse. So let me go ahead and show you that it actually does work, right? 85 times 2, they agree. The binary version took, well, 41, whatever that is, right? The base 10 version took less than half the time, and of course, just normal multiplication here was instantaneous. Let me kick that up. Instead of 2 digits, let's kick that up to 100 digits. And you'll start to see a huge difference here, right? The binary version is an order of magnitude worse, right? Now, this is just a Python thing, right? Now, I am sure that if you went down and did this in C or whatever and did some extreme optimization, that you could get better performance out of this thing. But the point is that there is this huge constant sitting in front that you are paying for the recursion. You are paying for so many more multiplications, or not multiplications, but you're paying for so many more operations like shifting. That does cost you something. You are paying for additions and subtractions, more additions, right? So there are other things that come into play in the real world from a practical point of view. There's some constant sitting out front that is huge. Now, if I keep going up, then you would expect that at some point you'll find the crossover point, where you have these very, very, very large numbers. The recursion starts to outperform, or the Karatsuba multiplication starts to outperform the traditional multiplication. Right? But I couldn't find that crossover, actually. I'm not even going to try that. I'll show you that it works for, well, I showed you it works for 100, right? 1,000. And you can kind of see a pattern here that it gets even worse, right? Almost a full second for the binary version, a fifth of a second for the base 10, and almost, again, instantaneous for the multiplication. Yeah?
How does the multiplication process work then if it took that short of a time to do?
You'd have to look under the hood, look at I don't know what version of Python this is, but you could, Python is open source. You can find out what, you'd have to rip open the code and start looking at their code to see what they do. Yeah. They might use convolutions or something like that. In fact, I'll note that here. Is there a better way? There are even better ways than this, by the way. There's Tomb Cook. Karatsuba multiplication goes back to, what was the year on that? I don't even have the year on it, but this is back in the 60s or so. There was a Tomb Cook algorithm that is even better. It's, well, 1963. It's going to be order n to the 1.4565. There we go. And to the, there we go. And then, of course, Strassen, based on in 1968, based on the fast Fourier transform (FFT), they came up with something that was very, very close to optimal, which is going to be order n times log n times log of n. I've got to fix all that. There we go. There we go. So n log n is actually probably the best you can do. I think that there might be a lower bound argument based on that. Like similar to, there's a lower bound argument for comparison-based sorting algorithms. Ideally, it would be order n because you have to look at all the input at least once. But there is a lower bound that you can actually prove that it's n log n. So for example, tim sort, merge sort, quick sort, those are all optimal sorting algorithms. Their behavior matches the provable lower bound. You can't get any better than that using a comparison-based sorting algorithm. There might be another lower bound for multiplication that says n log n. And it was finally reached. Well, actually, there's another step here. If you're in 2006, I think it was, what do my notes say? 2007, right? He got it down to, and this is, I only mention this because it's kind of interesting, a log n times, so let me go ahead and put in a c dot there, 2 to the log star n. Yep, there we go. So does anybody, has anybody ever seen that before? Log to star? So it's the number of times that you have to apply the logarithm function to get down to 1, right? So do I have a web browser open? Here we go. All right, Wolfram Alpha. So give me a number. Oh. Give me a bigger number. Come on.
1,632,000.
Well, if Wolfram Alpha, fine, come on. All right, there, finally. Log base 2 of, well, let's go with 1,024, right? That's 10, right? So I'm not at 1 yet. So apply the logarithm function again. Where am I? 3. Apply it again. Log base 2 of this. Now I'm at 1.7. If I do it one more time, what's going to happen? Now I'm less than 1. All right? So how many times did I have to apply the logarithm function to 1024 to get down to 1 or less? 4. So the iterated log value of 1024 is 4. Now let's go with yours. What did you say? 1 million what?
632.
1,632,000. Right? So I'm not to 1 yet, but you are several orders of magnitude larger, right? And so its iterated log value is only 5. Right? You could probably go even further here. Are you going to support that?
So the log star is replaced.
I could just mash the keyboard. I would have to mash the keyboard quite a while to get up to the next value, 6. So for all intents and purposes, does this term exist? Not really. Not for any practical values that you'd ever want to run on it in the real world. Right? Things going beyond the size of the universe, sure, but for no practical purposes does it matter. Yeah, go ahead.
So the log star is just replaced with like a 4 or something.
Yep.
So it would be like 2 to the power of 4 times n.
And that would get you for any n values that you would ever compute within your lifetime. Right? And then it would just be a constant. You could treat it basically as a constant. In 2019, they finally reached optimality. And they finally found an algorithm, and I forget the names, log n. But somebody finally reached the lower bound, I believe, of n log n. And they use a different convolution or a different transform, I believe. But it's all really, really high-level math stuff. Right?
Well, I hope that guy's a millionaire.
Nope, definitely not a millionaire because it's not really even all that practical. Fast Fourier transforms are very practical in practice. Fast Fourier transforms are something that if I were to say doing computer science 4, we would go over or something like that. I'd have to really teach myself some deep stuff, but there are also some nice visualizations of fast Fourier transforms out there, or Fourier transforms. Basically, the best one that I've seen is how you can draw arbitrary curves by simply just adding in another polynomial, right? And it's all approximation. Actually, you don't even add in a polynomial, you add in a rotation. So here's, you start at the center, and here's something going around at some period. You add something to the tip of it with a different rotation, and you can kind of start drawing, what is that? What is that kid's spirograph, right? It starts kind of looking like a spirograph. Add another one, add another one, add another one, until you can approximate any kind of curve that you want, right? But those are Fourier transforms. Again, it goes beyond the scope of this course. What I want to show you, oh, and by the way, let's go back to Karatsuba here. How the heck did he come up with this idea? How does any mathematician come up with their ideas? Mathematicians don't come up with ideas by simply just thinking about it. Oh yeah, here's a genius insight. They sit, that's why they have these whiteboards and these blackboards. They sit and they try a million things until they find something that works, right? And so he probably just sat there with a bunch of algebra until he found something that works, right? Oh, okay, I can get down to 3 multiplications by exploiting this Weyl rule, right? And that's exactly how Strassen's matrix multiplication works too. So Strassen's matrix multiplication. These mathematicians just sit there. I mean, you never see their failures because they don't publish failures. Nobody publishes failures, right? They sit there and they try a million things until something actually works, and that's the one thing that they show to the world. So it's not like these people were huge geniuses. They're very, very smart. I'm sure that some of them might be called geniuses or something like that, but it was just a lot of hard work and a lot of failure until they found something that actually worked, right? Strassen's matrix multiplication was very, very similar. I'm sure that he just sat there and he tried a bunch of just different matrix identities until he came up with this idea, right? Before we talk about the idea, we need to make sure that we remember how matrix multiplication works. So let's just do this with a 2 by 2 matrix. A, B, C, D, E, F, G, H. Multiply these two matrices together. What do you get? Well, you get a 2 by 2 matrix, right? And what's the upper left entry? You take these two things, and then you flip them, and you multiply component-wise these two things over here. So you have AE plus BG. What about this entry over here? Again, first row, now second column. Right? So it'll be A F plus BH. Okay? This one, CD, with the first column, gives you this entry over here. So CE, DH, add them together. And the last one is going to be CF, DH.
The one in the lower left.
Lower left is wrong. What did I do?
Is CEDG.
CEDG, you're right. Sorry. There we go. All right. So now for that 2 by 2, let's make some observations here. How many multiplications did I end up having to do? And here, forget about how many digits there are. Just straight up multiplications. 8. 8 multiplications. How many additions? 4 additions. Okay? Now let's generalize. So suppose that I had an n by n matrix, A and B, and I wanted to multiply those two together. Again, the same basic idea, but you take the first, oops, sorry, undo that. You take the first row and you multiply it by the first column, and that gives you the first entry right here?
Is it 4n squared something?
Well, let's be more methodical about this. How many entries are in the result? How many entries are in the C? N by n. So there are, I'll switch back over here. There are n squared entries in C. So how many operations to do just one entry? Let's look at this one case. How many numbers are here? N. How many numbers are here? N. So how many multiplications for that one entry? There are n multiplications. And how many additions? To add n minus 1. Why? Because n, well, if you've got 4 things, how do you add them together? 1, 2, 3 additions. So 1 fewer addition. Right? So n minus 1 additions. Right? So since you have to do that for each entry, in total, how many do you have? N cubed multiplications and n squared times n minus 1 additions. So which one of those do you want to focus on? Multiplications or additions? Which one is more expensive? Multiplications. Why? Because it's iterated addition. Right? 4 times x, you take and you add x to itself 3 times. Right? Or 3 additions. So definitely want to probably focus on multiplications here, in which case this leads to an order. It doesn't really matter. If you look at the other one, it's the same analysis. It's going to be n cubed. Okay? Now, what is the input size in this thing? Got to be careful. Careful. What is the input? 2 matrices. Both of them are n by n matrices. What is the input size? N squared. In fact, 2n squared because you have 2 matrices, right? 2n squared numbers. So if we have an algorithm that operates in order n cubed, n is not our input size. At least you're telling me that n is not the input size. Let's go ahead and give it a different name. N is our input size, and it is n squared. Without loss of generality, go ahead and ignore that too. Right? So what is our true complexity here? N to the 1.5. So in other words, it's already sub-quadratic. It's not actually a cubic algorithm because the input size is n squared, right? All right, so this is a technicality, right? Technicality, right? Without loss of generality, we'll assume the input size is n. Why? Because you can always take it and divide it by n to the n squared, right? Who cares? It's still going to be polynomial. All right, so I don't like writing it out, so I'm just going to go ahead and import it here. Strassen came along, and I would go into more detail, by the way, if this was one of the programming assignments. I've done that before and assigned Strassen, but I did not do that this year or this fall. Instead, you're doing something else with matrices. So here's Strassen again. He came up with, he started writing these things down on a blackboard, started rearranging, and he finally came up with this following identity, right? That if you compute these 7 numbers here, excuse me, then what you can do is you can come up with A times B, these are matrices, is equal to, and all you have to do is apply these identities in the following order. M1 plus M4 minus M5 plus M7. Right? That's the upper left entry. M2 plus M4 in the lower left, and M3 plus M5 in the upper right, M1 plus M3 minus M2 plus M6 in the lower right. Okay? Now, this works on scalar values, if each one of these things is actually a single number, or it works on the idea that you can take an entire matrix and split it up into quadrants. This will be a not. Right? If you take, say, a 64 by 64, what you can do is you can look at a subquadrant here that is 32 by 32. And then you can recursively apply all 7 of these matrices, use them to compute, actually compute, you know, the upper quadrant of this matrix, the upper quadrant of this one. So you might imagine, well, wait a second, what if I did this with 64, 32, 16, 8. What if it was not a perfect power of 2? What could you do? Yeah, pad it out with a bunch of zeros. And if you were to actually program this, that's exactly what you would do. If you had a 5 by 5, well, what's the next power of 2? 8. So you pad it out with a bunch of zeros, pad it out with a bunch of zeros, right? And then once you've padded it out, now you've got a perfect power of 2. When you're done doing your multiplication, you return from the recursion, you simply just cut those out. And it's the same answer. It'll all be zeros anyway, because 0 times 0 is going to be 0. Right? You had a question?
Does it only work for square matrices?
Well, that, if it does, no, I think
It's a valid operation. Does it work for?
I think it will. You just need to pad it out. You pad it out so that it is a square matrix, and then undo the pad. Yes, I believe it will. All right, so did Strassen come up with a better way? How many multiplications are we doing now? Well, do we do any multiplications down here? Nope. We just do 1, 2, 3, 4, 5, 6, 7 multiplications. So 7 multiplications. How many additions, though? Let's keep track of that. I see an addition here and here and here, so that's 3 so far. What about this thing right here? Is that an addition? Yeah. How is this an addition with its subtraction? It's an addition by a negation, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 additions. Now, compare that with the 2 by 2 case. The 2 by 2 case that we started out with, we had 8 multiplications and 4 additions. And now we've got, what? 7 multiplications. So we've cut it from 8 down to 7, right? But what have we done to our additions? Yeah, just a little, right? It went from 4 up to 18. But you said multiplications were way more expensive, right? So maybe this trade-off is okay. Let's think about this in terms of a divide and conquer strategy. Again, let's go ahead and set up an m sub n to be the number of multiplications by Strassen. Now, how many did I need to make a recursive call on? There were how many recursive calls? 7. 1 for each one of these submatrices. Right? On inputs, how big? Well, if the sizes were n squared, now they're correct. N squared goes down to n squared divided by 4. Okay. Now let's get that into a, without loss of generality, let's assume that our input is n. So take a square out of that denominator, and what do you have? N over 2. I'll leave it there as squared, right? But now, again, without loss of generality, go ahead and screw that square term right there, right? Without loss of generality, right? N divided by 2. Did we do any non-recursive multiplications? Nope, it was just like Karatsuba. We ended up doing the actual multiplications in the base case when we got down to a certain size. If you've got a matrix, a 2 by 2 matrix, that goes down to a 1 by 1 matrix. How do you do multiplication of a 1 by 1 matrix? A and B. They're just scalars at that point. A times B. Right? So 0. And again, the master theorem here is A going to be 7, B is going to be 2, and D is going to be 0. So 7 versus 2 to the D. Same exact case as before. That's the third case. And so M sub n is going to be order n to the log base 2 of 7. Now, without pulling out your calculators, I can tell you that that is definitely going to be less than 3. Right? What is it, in fact? This is approximately order n to the 2.807, right? Versus order n cubed. Now, unlike multiplication in the fast Fourier transform, we still do not have an optimal algorithm, right? There is another algorithm that's kind of old, the Vinogard algorithm, that uses different, a different chalkboard full of identities to get it down to order, what is it, n to the 2.375477. And then there was further analysis done to show that the exact same algorithm, there was no change to the algorithm, but a little bit tighter analysis got it down to order n to the 2.3727. So several thousandths less. And this is the last one that I'm aware of in 2012, right, by Williams. Right? So again, divide and conquer, divide and conquer. Do you think that without me having to write Strassen's algorithm, do you think that it's going to be better in practice? Probably not. Same situation as this, right? Where the overhead required to do the recursion and the extra steps required to do the identities and stuff like that contribute to this constant that's sitting out front. That constant is only eclipsed with huge matrices, right? And at that point, there are probably better heuristics to apply than these algorithms. But the same idea, can you use divide and conquer to get down below the naive way of doing things? Right? And yes, you can, theoretically. So, do you want to implement it? I have assigned it before, but yeah, go ahead.
I have a question. Why did you divide by, so n squared divided by 4, why is it again? So 7n and then...
Because how big are these matrices? So if it's an n by n matrix, and I split it up into 4 parts, how big was it before? N squared. So how big is each one of these parts? N divided by 4, which is equal to n over 2 squared. And again, without loss of generality, we'll assume that n is our actual input size, in which case I can say, forget about that. If you don't want to forget about that, that's fine. At the end of the day, do the trick that we did before, where we rewrite the input size to be n squared. Your last analysis, you will divide by n squared, and you'll get a different number. Right? You have to compare apples to apples and oranges to oranges, though, right? You can't compare the naive way of doing it, n to the 1.5, and the Vinogard method, right? Because that says that the naive way of doing it is better. You'd also have to do the same thing here, where you divide by n squared. And now it gets it down to n to the 1.2 something something something. 2? 1.1, whatever it is. Right? You can't cheat and compare your apples to those oranges. My apples are better than your oranges.
Is that why the Apple is Samsung debate still goes on?
I have no idea. I only have I have a $50 Android phone. All right, then we'll continue. Oh, actually, no. We'll move on to something else matrix related next time.